All right. So we are on YouTube Live. All right, great. And now it's 1:03, so let's see who else joined us in Zoom. All right, so people joined us. I see Elizabeth. Welcome, Elizabeth. Welcome, Paige. Welcome, Aquila. Welcome. So, all right, we are at week 4, guys. Thank you guys so much for rocking with me from the beginning. So we've been doing this for 4 weeks in a row right now, and I said it's, you know, it's my Valentine gift to you guys, right? The month of February, free chemistry. But February is finished now, and so I now have a vested interest in you guys succeeding. I feel like I can't just leave you high and dry. Like I have to do something, right? After when February ends, because today is the last free class, right? So there's March and there's April and there's May, and the exam is in May. I think I told you guys the dates at the beginning, that first week. I can't remember it off the top of my head what the dates are, but it's May, early May. First week May, second week May, paper 2, right? Paper 3 and paper 1 is later on, but the bulk of the stuff, paper 2 stuff, that's the bulk of your grade, right? How you do in paper 2 really determines your grade for the most part, right? And that's like early May. So, I mean, I'm gonna talk about what I have planned for the rest, like leading up to the exam after this free series ends for February. And so I'll just talk with you guys at the end of the class about what that might look like going forward. And then today, what I have planned for today is, last time, can you guys hear me? For some reason, I feel low. Like I feel like I'm talking low. I don't know why. I hope you can hear me. Because I'm not hearing you guys either. If you're saying something, I don't know. So where was I? Yeah, okay. So Elizabeth says she's hearing. Okay. So for today, which is the last day, last week, week 4 of LMD and Chemistry Sundays. Last week we wrapped up. We done mole concept up to the point where we were like doing these intricate equations that were like, you know, trying to figure out limiting reagents. We're trying to figure out how much product you can get from certain reactants, and if you got a certain amount of product, what might you have started with from a reactant standpoint. So we did that. And so now we're ready to move on to oxidation and reduction reactions. However, I'm realizing that there is this concept or this topic that while it is not directly underneath mole concept per se, or depends on the book that you're using, it involves a lot of moles. And so I wanted to just like go through that like very quickly with you guys. So it's something called acid-base titrations. You've probably heard of it, or if you've done a past paper to this point, you've definitely encountered it, because it's typically the very first question on paper 2. Right? They'll give you experimental data from a titration, and they'll say, oh, do this calculation, figure out the molar concentration or the volume. So I wanted to touch on that real quick with you guys today before jumping into oxidation reduction reactions. What do you guys think about that? Give me a thumbs up or unmute and tell me what you think about that. So my plan is just to do acid-base titration, which is an extension of mole concept, and then move on. Okay, I see those thumbs up. So yes, okay, great. So let me share my screen then. Slideshow from current slide. All right, so now I'm sharing my acid-base titration slides with you. Okay, so we are in it now, guys. So as I said, acid-base titrations falls largely under acids, bases, and salts, that topic. But I think it's important to teach it to you guys, because I'm not going to touch acid, bases, and salt for this. It's the last week, right? But I wanted to touch on it for you guys, since I am helping you guys to build a solid foundation in moles. I felt like it would be negligent of me to not share this part with you. Okay, so acid-base titrations now. So the idea behind this, or how this works, is on the basis of a neutralization reaction, right? And a neutralization reaction is a reaction between an acid and a base, right? And can any one of you bright students tell me what the product is of an acid reacting with a base? What do you typically get from that neutralization reaction?
Salt and water.
Salt and water.
Exactly, that's exactly right. So you get salt and water. When the acid and the base react, it's completely neutralized, and that's what you get, right?
Yeah.
So the acid-base titration is like the basis. It's like that's the reaction that defines the titration, right? So the titration, if we're defining it, is really used to determine the amount of a substance. So the amount of a substance from a concentration standpoint that's present in a given volume of solution of acid or alkali. So that whole thing is a concentration. So the amount of stuff that you have per unit volume, right? So that's what the concentration is. And so let me bring this up here so I can show you. Well, maybe here. Okay, I'll just put it back here. Okay, so right here on the right hand side, you can see, you see this picture here, right? So you have your burette, you have your tripod stand, you have this conical flask here, and you notice that you have something in it, right? So typically in a titration, what would happen is you have, so say, just for argument's sake that we have, or acid-base indicator, more than likely that's something called phenolphthalein, that's that pink color there. And you have, so you have an acid that's in that conical flask, right? But you don't know the concentration of that, what exactly is in that conical flask. So what you're gonna do is maybe you'll add a base, right? And then what you're doing is recording from that burette how much volume of that base you needed to add to have that color change take place, right? Because the color change indicates an endpoint. So that's when you're completely neutralize the acid with the base. So that's typically how titration works. You have something in a conical flask where you don't know exactly how much of it, and you might not even know what it is, but you just know it's an acid or a base, right? And then you're gonna add something, a base, from the burette, and then you're gonna make note of where you start and where you stop, so you know what the volume added is. And then based on that, and based on maybe you know the volume of this stuff in the conical flask, and you know the concentration of the base that you added along with the volume, then you'll be able to find out what the concentration of the stuff in your conical flask is. Does that make sense? So that's a general idea behind these titrations. And this is like, if you go through past papers, I guarantee you will see that the first question typically is something like this. Let me see if I have one right here, I can tell you. So they'll give you like the volumes and volume used, and then they'll be like, oh, tell me what's the concentration of whatever I added it to, right? So that's this whole idea of titration. I'm looking if I see a past paper. Oh yeah. See, I skipped one, I just flipped to one, and it's the exact same thing. Volume of base added, I'll show you. I'm gonna just like turn this around and show you guys real quick, because it's like, it's everywhere, right? No, we haven't done any past papers for these things, for this LMD and chemistry Sunday, because we don't have time, and I really want to get you guys learning the concepts. But like, let me show you this past paper, how like the very first thing is one of those things. So look at this. Can you see that? Volume of base added, right? And they're telling you the pH reading. So you're trying to figure out like when the color change, or when there was a change in the pH of the solution, to figure out endpoints, right? So these are typical things that you'll get on CXC. Paper 2, first question, guys. So I want to go through it. So we have acid-base indicators that tell us when the endpoint of the reaction is reached, right? And the endpoint is just where you see that where the acid completely neutralized by the base or the alkali. Can anybody tell me what an alkali is? Like what's the difference between a base and an alkali?
An alkali can dissolve in water.
That's exactly right, Jada. So alkali is soluble in water. So if we have a base that dissolves, you have a base that's dissolved in water, that's an alkali, right? So that's that would be like, we'd call it an alkaline solution. And just to kind of show you guys just how chemistry is everywhere, when we think about our biochemical makeup or our bodies, we are doctors or scientists often encourage us to maintain an alkaline pH in our bodies, because that's more conducive to the bodily functions that it's conducive to keeping a stress-free body, right? So like a lot of, when you're under stress, the pH of your body changes to acidic, and that's not good. You get sick from that, right? So that's like stress, the food that you eat. If you eat too much acidic food, it will make your overall pH of your body low, which is an acidic pH, right? pH acidic is acids of low pH, alkalis of high pH, or 7 and above, right? Are alkali solutions. But we are supposed to have in our bodies alkali pH, so above 7. And the way you do that is you don't stress out yourself, don't put yourself under stress, and you eat foods that are alkali forming, right? Alkali forming foods. So that's just a little bit of a diversion, but I wanted to just show you guys how this chemistry stuff is everywhere, right? All right, so that's about alkalis. And alkali is just a base that's soluble in water, as Jada correctly said. So we have acid-base indicators, and these tell us when the endpoint of the reaction is reached. The endpoint is when the acid has just completely reacted with the alkali. So like it's like a snapshot, like right now, and then you have to turn the burette like that same time. You don't want to put too much stuff in it, right? Because then you overshoot it. So like the endpoint is like right at which the neutralization has taken place, right? And you see all these lovely colors here. These are all the different acid-base indicators that we can choose from to determine endpoints. Can anybody name their favorite indicator or any indicator that you know and tell me?
The orange.
What's it called? You know what it's called, orange one?
Methyl. Oh, the word here.
It's like there's so many of them. There's so many of them. However, there are some that are more commonly used, you know?
Like the
phenolphthalein, right?
Yes, miss.
Yeah, that's a very common one. I'm looking here to see if I can see any other common ones that I can just shout out the name for you. So that when you go in an exam and you see that, even if it's just like multiple choice, you'll be like, oh yeah, that's an indicator. So it's a titration. So I need to do X, Y, Z, right? So that's just like, I just gave you like a high level explanation as to how titrations work, but definitely, because we're not going to cover it here, go back and look a little bit more deeper into it, right? So it's just a definition for the intents and purposes of what I'm going to teach you today. All right, so see it here now. Guys, the common one is litmus paper. And what happens with litmus paper? Like if it's in acidic solution, what color is it? And if it's in basic, what color is it? Litmus paper. Tell me about that one. Britannia said litmus. So Britannia, tell me then. Well, litmus paper is what color when it's in acidic conditions, and what color is it in basic conditions?
When it is in acidicness, it is red, and when it is in alkalineness, it is blue.
Exactly. So that's an example of an acid-base indicator. And then phenolphthalein, that's very common too. It's a hard word to pronounce and spell, but that's very common. And so when phenolphthalein is in acidic solution, it's colorless. And then when it's in alkaline solution, it's pink. So you might imagine that this particular thing that I'm showing you here, it was colorless before, and you added your phenolphthalein It was colorless before. So like say you have your acid, right? And you have phenolphthalein in there as well as an indicator. And then you add base. So it's completely neutralized. And that's when you have that color change from colorless to pink. Does that make sense? So this one I think is phenolphthalein that was in this conical flask. And then you have methyl orange. Is that what you were referring to, Aquila? Methyl orange?
Yes, miss. It's just the method when you want to get a correct pronunciation, but yeah, that's it.
Yeah, so it's methyl orange, and you have screed methyl orange, and you have bromothymol blue. Like, this is bringing back memories, guys. I remember these. Like, these were the ones that we did. So litmus, phenolphthalein, what's the other one? Litmus, phenolphthalein, methyl orange, screen methyl orange, and bromomethyl blue. So just like jot those down in your notes, and then you can go back and look at it after class, right? But those are the common acid-base indicators. And then some definitions again, guys. I have to tell you these definitions, like as I said that first week, definitions aren't everything, but you have to know them. Like, you have to know things are defined, otherwise you're not going to be able to do the problem. You're not going to be able to start, right? Because oftentimes, deeply embedded in these definitions are the actual equations, if you think about it. So think about it. Look at what I mean by that. All right. So here we're defining a solution concentration. I didn't teach you guys about this before. I taught you about like moles, molar volume, molar mass, but I never thought about this is a new concept that I'm teaching you. You're probably aware of it from your classes, but I'm teaching you for the first time. Concentration, right? So you have a solution concentration, that's the broad heading, and then within that you have a molar concentration. And that is the number of moles of a solute. You remember your solute, what a solute is, right? A solute is dissolved in a solvent, right? And that makes that molar concentration definition, and is that the number of moles of a solute dissolved in a solvent to make 1 decimeter cubed of a solution, right? So the molar concentration is the number of moles of a solute dissolved now in a solvent to make 1 decimeter cubed of a solution. And so in that, you can see that these units then make sense, right? So it's the number of moles of stuff dissolved in a solution that make 1 dm cube of a solution. So it's the number of moles per dm cube, right? So that's the unit of molar concentration, right? So this is very important, guys. So does this make sense? It's very important before I build on this, right? So that's your molar concentration. And then we have these definitions / formulas here that kind of are extensions of that definition up here, right? So it says that the concentration is the mole in units of mole per dm cubed, right? Is the number of moles of solute in moles per volume of solution, right? So if you do per volume of solution, that's how you end up with the amount that make 1 dm cube, right? So per volume of solution, that would give you that molar concentration. So that's what this is, right? Number of moles of solute per volume of solution. Then you have a mass concentration, right? And that mass concentration is the mass of solute in grams divided by the volume of solution in decimeter cube. So can somebody, one of you brilliant students, tell me, how would you make this conversion from here to here? How would you go from like the molar concentration to the mass concentration? What would be your factor? What would you multiply by? What would you divide by? How would you make this jump from molar concentration to mass concentration? Anybody? How do you make that jump? It's not a trick question. It's not a trick question, right? Number of moles, look at the bottom. The bottom is the same, you know. The bottom is still the volume of solution because that's a concentration thing. It's per volume. but you can either have a molar concentration or a mass concentration. So if I gave you a molar concentration, how would you convert that to a mass concentration? And similarly, how would you go back from a mass concentration to a molar concentration? Any takers? It's not a trick. This is not a trick question.
You'd multiply to go to the mass concentration, you multiply the molar mass.
Multiply by the molar mass. So let me just get my pencil real quick and see what Kaylee is saying here. So she's saying you multiply this by molar mass and the units of that is in what? You guys know how I love to like mess around with units to show you, all right? So that would mean that, oh Lord, not today. It's saying my internet connection is unstable. I really hope it doesn't fail me. All right, so you see that now? The moles cancel and you get grams per dm cube, which is exactly here. Does everybody see that? So if you want to go from here to here, you multiply by this. See that? So that would give you those units now. You see that? So you multiply by the molar mass, as Kaylee rightfully said. You multiply the molar concentration by a molar mass, and that gives you your mass concentration. So if you want to go the other way, so you want to then go from here to here, what would you do?
So you divide by the molar mass.
You divide by the molar mass, and so let's see what that would look like from a unit standpoint. You see how, guys, you see how important units are? Like if you're lost, the units can help you. That's all I'm saying. Like if you're lost, the units can help you. Because I'm just checking what Kaylee said against the units that I know they're supposed to have, right? And we know they're supposed to have because it's on the screen. Let me see where my pencil is. Okay, so look at these units now. So the mass concentration is grams per dm cubed, and we're trying to get to moles per dm cube, and Kaylee is saying that we divide. So if we divide by it, we would divide by units of gram per mole. And of course, by the math rule, you know that you'd have to bring that mole up top. So you'd have gram dm cubed times, right? You do like your, it's a reciprocal thing now, right? You see that? And the grams cancel. Oh, not that. This. The grams cancel. So you get mole per dm cube. Does everybody follow that? Just remember these. You have to remember these, you know, guys. You have to remember these conversions because sometimes they'll give you a mass concentration and you have to be able to find out the molar concentration or vice versa. So that's why I'm showing you how this actually works, right? Brittany said, okay, so let me go over it then. All right, let me go over it. Let me I get my mouse. Do I have my mouse? Okay, I have my mouse. Okay, so what I'm saying is you have two types of concentrations for intents and purposes of what we're doing here, right? Concentration is just the amount of stuff per unit volume. But when we talk about a molar concentration, it's the number of moles of solute dissolved in a solvent to make 1 decimeter cubed of a solution, right? So the units are mole per dm cube. And then you have this formula here that lays it out nicely, that definition for you that says the number of moles of solute divided by the volume of solution is what would give you your concentration. And those units are in mole per dm cubed, right? Then down here, you have this idea of a mass concentration, not a molar, no, you know, a mass concentration. And that's why I'm showing you guys that this builds directly on what we did with mole concepts, right? So you know you have a mass concentration and that unit is in grams per dm cube. So literally, if you compare this equation up here and this equation down here, the only difference is that this is in mass and this is in moles. But you guys know from mole concept and our 3 weeks spent on mole concept that if you want to go from moles to mass, you would multiply by the molar mass. And so that's exactly what we did here. As Kalia said, we multiply our molar concentration, this whole thing, by our molar mass. And so from a unit standpoint, what you see is that the moles cancel out each other and you're left with gram per dm cube, which is exactly the units of mass concentration. Is that clear, Britannia? Okay, so that's clear to Britannia. Is that clear to everyone else as well?
So far, miss.
What was that?
So far.
Okay, and so then just to continue and then we move on. So by that same analysis, right? If when we were doing mole concept, if I wanted to go from mass to moles, I would do my given mass divided by my molar mass. And that's exactly what you do here as well. You have your mass concentration and it's mass of solute divided by volume of solution. So you're doing, so these are your units, gram per dm cube, and you're dividing by a molar mass. So then when you go over here, and I'll just like show you how it works out, grams per dm cube, you know, you're gonna flip when you're doing division, right? That's just some math stuff. So you multiply by mole over gram. From a unit standpoint, that's what it looks like, right? So the grams cancel and you end up with moles per dm cube, and that's exactly what this is. So you're going to go this way, you multiply by molar mass. To go back this way, you divide by molar mass. So is that clear to everyone? Janelle, is that clear, or do you want me to go over it again? Guys, if you don't understand, let me know, let me know if you don't understand.
Miss, you can go over it again, please, because my internet just went away and I had to put on service.
Okay. All right, so we can go over it again now. All right. Concentration, the number of stuff that we have per volume. That's concentration at a high level. Now we're saying, oh, a molar concentration is what we want, or we want to talk about a molar concentration. So that's the number of moles of solute that we have, right? And remember that the solute is the minority part when you have a solution, right? So the minority part is the solute and the majority part is the solvent. Typically, it's liquid, but it doesn't have to be. It can be gas. Your solvent can be a gas because you have gases dissolving in gases. It happens in the atmosphere, right? So that's just definition for solute versus solvent, right? So just brushing you guys upon that, you have a solute and you have a solvent. In this particular case, or for acid-basis titration, your solvent is typically, it's a liquid, right? It's a liquid. So you have a solute, right? And you're putting that solute in a solvent, and the number of moles of that solute that you dissolve in that solvent to make 1 decimeter cube of that entire solution is what you call your molar concentration. Now, molar concentration, you have molar concentration. Similarly, we did it for mole concept. You know, you have your moles and then you have your mass, right? And that's the typical, the common conversion that we do. You have your molar concentration, and that's the number of moles of solute per volume of solution. So that unit is mole per dm cube. Right? So now, going back to mole concept, whenever you want to go from moles to mass, right? If I give you 10 moles and you want to go to find out how much mass of the stuff that is, you would multiply by the molar mass, which is just the mass of 1 mole of the stuff, right? So this is what the molar mass is, the mass of 1 mole of the stuff. So it's a gram per mole. That's the units, right? So then if I multiply by the molar mass, which has units of gram per mole, and this has units of mole per dm cube, then I can cancel the moles then, and I'll get gram per dm cube, and that's exactly what we want for this mass concentration. Right? Elizabeth, Janelle, you guys said you guys wanted me to go over it again. Is that clear?
Yes, miss.
Okay, and then to go the other way now, you're going from mass concentration back to molar concentration. When you're doing mole concept, if you want to go from your given mass, right, 2 moles, what would you do? You divide by your molar mass, and that's exactly what you do here as well. This is your given mass concentration. You want to go to molar concentration, so you divide by the molar mass, which has units of gram per mole, and then you go over here, grams cancel grams, you get mole per dm cubed. That's exactly what we want, right? Is that clear? Let me see what is being said. Let me see. Okay, so I can see all of you now. Thumbs up if that's clear. Jabari says that's clear. I see your thumbs up. Let me see thumbs up, thumbs down, and then we move on. Britannia says good day. Chanel, Kelia, Adam, Daniel, Claude, Jabari says okay. Jamar, I'm not hearing you guys. Let me hear from you guys. Let me see those thumbs up so I can know to move on. Okay, I think I've seen every thumbs up now. Okay. Kayola, welcome Kayola. Claude says it's clear. All right, boom. That's what I want to hear. All right, so we can clear this now, and then let's see what we have next. Maybe we'll just jump into some problems on this and then move on. All right. So we have problems now, guys, because that's really like if you know the definition and you know you have a good foundation, you'll be able to do the problem. So now we're in a problem. So who wants to take this one? Remember, I want you guys to participate, you know. And in light of today being the last day, I should have a nice little gift because I haven't given before for people who participate. So who wants to take on this? In light of how we just did those definitions and that explanation, can anybody take on this problem? Let me see. And while you're doing it, I'll be thinking of how I might compensate you. The people from last week, I haven't forgotten about you. Your session is coming. It is coming. So be thinking about what you want to discuss with me so that you can make the most of it. But the people from last week, there are 4 of you, and I haven't forgotten about you. It's Paige, Jemar, Jabari, and Chanel. I haven't forgotten. So you guys, you can answer this week, but like I want other people, because you already win your free session, okay? So anybody else here who wants to answer this, please go ahead. Please unmute yourself. Please write on my screen. I want to know that I am moving the needle in your knowledge, and so I want you to do this. I don't want to tell you how to do it because I think you know how to. Just calculate the concentration of a solution of sodium hydroxide, and they're telling you this number here, which is the relative molecular mass of sodium hydroxide, right? Because this is a molecular compound now, right? Sodium hydroxide. So that's why they give you MR, relative molecular mass, and that's 40, right? They're telling you there, 40 gram per mole. And then containing 0.60 grams of sodium hydroxide. So that's a mass, guys. I'm breaking it down for you, and I'm breaking it down nicely. I'm showing you what you have. And then all you have to do is just multiply. But I don't want you guys to just use the formula. Think of it like critically and think of what you're doing, right? In terms of the definition that I just gave you. So like, okay, we have mass here. And then what is this, guys? This is a what? This is a unit of what? The cm cube is what? This is a volume, right? Are you guys there? You're awfully quiet. Like, it scares me when you're that quiet because I don't know if my Wi-Fi has shipped out. So please say something so I know that you're there and that we are still in this thing.
Yes, miss.
Okay. All right. So guys, you have everything that you need to find the concentration of the solution. And I hope that you're never completely lost, but if you are, you can just mess around with units and you will get the answer, right? So I'm not gonna talk anymore. I want somebody to do this. So I see that you're actually understanding it. Like, I've done my part here. I've like given you all the important pieces of information in this question. that you need to calculate the concentration. So who will step up to the plate and do it? And if it is that it's somebody from last week who already got a free session with me, maybe I'll give you something else, something extra, right? To push you further in your chemistry knowledge. So if it is that you answered last week and I said that you shouldn't answer again because you win already, if you're the only person who is brave enough to answer right now, I will reward you, okay? So if you want to do it, because nobody's answering and I want you guys to do it. I don't want to do it. I don't want to spoon feed it to you. I want you guys to take a shot at it, right? You have mass, you have volume, you have a molar mass, right? That slide that we spent all the time on a while ago, you have everything that you need to do this. Trust yourself, step out in faith and solve the problem, right? Who is going to do it? Who is going to do it? Unmute yourself and tell me that you're brave enough to tackle this problem. Or is it too simple for you? Are you just like, Miss, that's easy. Something. What do you want me to do that for? Miss, that's simple thing. Is that what it is? Because nobody's answering. And I'm like, am I like teaching them basic things that they're just kind of like, I'm over that, Miss. What do you do? Like, if that's the case, let me know. Because no answer. And I don't know what's going on. All right. Janelle says she wants to do it. All right, Janelle, come through. Come through, Janelle. Answer it first. Well, you have to write on my screen though. Or as you're writing, let me know why you're doing what you're doing, okay? So Janelle has her hand raised. Is that why you raise your hand, Janelle? Do you want to do it?
Yes, I could try.
All right, that's what I like to hear. Give it a shot and talk us through what you're doing.
You write for me. I don't know how to write.
What was that?
You write for me, please.
Okay. All right, let me get my stuff. Let me get my pencil because let me get my pencil straight. All right, let me choose a different color. So I'm gonna write in royal blue. All right, ready. Talk me through what you want me to do. What are we doing here, Janelle?
Yes, I think we could find for one. How much could be in one DMQ?
DMQ?
Mr. C, if it's at SCPO.
Oh, so for these ones, okay. So like I think for these kinds of calculation, you don't really concern yourself too much with STP or RTP. Like if that was the concern, they would tell you, but typically these are standard, they call standard solutions, and it's a standard temperature, right? So to the extent that it's good that you know that they tell you that it's a standard solution. We're typically working with standard solutions when we do titrations, but that information, that knowledge kind of stops there, right? You're not needing to go from a volume to, you're not using concentrate, you're not using a volume. Let me say it like this. For these kinds of problems, right? You're not using a solution volume to find the number of moles. Does that make sense? You're using the solution volume to calculate the concentration. So it's not the same as what you were doing before in the regular mole concept where they would say, or the basic mole concept where they would say, oh, STP, if I give you this volume of gas, how many moles of gas is that? Like, that's not what you're doing here because its concentration is a bit more advanced. So the extent to which you need to find the moles here would be directly related to a given mass and a molar mass. Does that make sense? And then the volume is just what you need to divide by to get your concentration. So the first step here then is to find the number of moles of sodium hydroxide, right? Do you follow what I'm saying, Janelle, and everyone else? Do you follow that? The first step is to find number of moles of sodium hydroxide that you have. And because sodium hydroxide is not a gas, you don't need to do that STP stuff, right? It's a solution that's not gaseous. It's a liquid volume, right? So you can't really apply STP, RTP because that's largely for gases. Well, it is for gases. And there's no gas in this setup that we have here. Does that make sense?
Yeah, miss.
Okay, so your first step then is to find the number of moles of sodium hydroxide. So what's the number of moles of sodium hydroxide here? Given everything that you have on the screen, moles of NaOH is what you need to find first, right?
Miss, I think you're dividing.
So you do what?
You're dividing.
So you do to find the moles, you do given mass, so the mass that they give you, divided by the molar mass, right? So then I'm gonna write this again. What was that?
Divided by the 0.60. Is it the 40 going to be divided by 0.60?
Oh, so the 0.60 is gonna be divided by the 40, right?
Okay.
It's your given mass divided by your molar mass, right? Look at these units again. G per mole, right? That's what the molar mass is. And the mass is G, right? So then when we do that now, we're going to do G. So it's G divided by G per mole, which is G times mole per gram, right? And so the grams cancel and you end up with moles. So that's what we want. This is what we want. We want moles of NaOH. That's our first step in solving this problem, right? So that would be given mass, which is this 0.60. And you divide that by a molar mass, which is this 40 grams per mole.
I had it wrong here.
And what is that? Anybody have them calculator?
0.015.
Okay, so that's 0.015 moles. All right, so we have step one. Check. What's step two, guys? Anybody can tell me, because this is the final step now, you know. Well, there are two steps. Tell me the step two and then step three. There are two steps. And that step two is like tied up in the unit. Because this unit that we got for volume is in centimeter cube, but when we define our molar concentrations, it's always in decimeter cube. So you have to convert the 200 centimeter cube to decimeter cube. So what's that conversion? Go ahead, Elizabeth.
Miss, you're going to divide it?
So you divide what?
By times it.
I don't think that's right, Elizabeth. Think again.
By 1,000.
So you divide the 200 by 1,000 first, right? To get your DMQ, right? Is that what you're saying, Elizabeth?
Yes, miss.
Okay, so if you divide the 200 by 1,000, what do you get?
Miss 0.2.
0.2, and that is your volume in decimeter cube, right? I'm trying to find my pen. I don't know why this pen's always. Well, I hope you guys wrote that down. All right, so let me just start at step two. So step two now is the unit conversion, right? So let me just write that here. Unit conversion. right? So we're converting, let me get back my royal blue. So we're converting 200 centimeter cubed to dm cubed. And you guys said that that is 200 divided by 1,000. And that would be, what would that be, 0.2?
Yes, miss, 0.2.
So that's 0.2 dm cubed. Step 3. What's step 3, guys? That's the last step to get the concentration now. Step 3 is apply equation for concentration. What is that, guys? What is this? For concentration. So what is this, guys? Just shout it out now. You're home free now, you know. You have the answer now. So what is the equation? The equation is what? The equation for concentration is what? Concentration, and we just write the units again. Mole in a bracket, mole per dm cube. This is here the answer, you know, guys. Just the units alone, you know what you need to divide what by what. You see? What was the number of moles again? What was the number of moles that we got from step 1?
That would be
0.015.
0.015.
0.0155.
0.015 mole divided by that 0.
0.0.
dm cube. So what's our concentration now?
0.075.
0.075. All right, so that's your answer. Write it 0.07. And what are your units?
Would that be
Mole per
dm?
dm cube.
Mole per dm cube. That's exactly right. All right. So all right. Is that clear to everybody? Let me know. Let me know if that's clear. If it's not clear, let me know too. Okay. All right. Let me see what's going on in the chat. Daniel is giving answer. Jamar is giving answer. Kaylee. Okay, so that's good. I see those thumbs up. All right, let me clear my screen and move on. One more problem on this and then we move on. So like, guys, definitely in your own time, go a little bit deeper into this stuff, okay? On this idea of titrations. Do some titration problems. Well, I'll talk to you guys at the end about what I have planned for like preparing for like the exam, like past paper problems and so on, marathons and stuff like that. But like on your own, I really hope that you guys have your study plans already that you're following, right? I know that chemistry is not the only subject that you do. You have other subjects and you should have a study plan for all the other subjects, right? Like what topics you're doing, when you're doing it, and and checking things off on that checklist, right? Because the exam is coming up soon and you don't want to have to resit chemistry or anything, right? So just like take your time and study, right? Make your study plan and just work through the things. So that when exam come and gone, you know, they had a ball and everybody there to enjoy them summer. You have a ball because you have to go retake it. Nobody do that. So just study, make your plan so that, and work through your plan, do your past paper so that, you know, you can enjoy your summer, right? All summer long you can do on TikTok. Go viral on TikTok in the summer, but not right now. So don't waste your time on TikTok. Study, okay? And make a checklist. So when you're doing your past paper things, exactly, Aquila said, I don't want to resit. No, resitting is not your portion. You're not going to resit anything. You have to sit down and study though, so you don't have to resit it. All right, so that's that. Those are the formula that we used. And then I'm going to give you guys this problem. It's like, how do I say this now? Yeah, this one is a little bit more complex, but everything that you need is there, right? So, okay, let me know. I don't want to spoon feed it to you guys like I did just now. I want you guys to do it. I want you guys to look at everything that's there and then kind of like break it down into the pieces of interest, the pieces that you need to be able to do the problem. Like everything is there that you need. And I said, when in doubt, look at the units of things, right? So who wants to take a shot at this one? This one is a bit more complex than the one that we did last time, but not really, like not even. But I walked you through that one, so I think you're good to do this one now. So who wants to take the floor? You can write in a text box on my screen and just talk me through what you're doing. Elizabeth, I see that you're highlighted. Is it that you want to go ahead? Hey, you guys can go silent. Like they're just like silent. It's just like crickets. I don't hear anything. I don't see anything. And I'm just like, are they there? Jada is saying that you have to convert the 50 centimeter cube to dm cube, right? That's good. That's a good first start. That's a start. So let me write that then as step one in this case. So Jada, step one would be to convert 50 cm cube to dm cube. So then to do that, you divide by 1,000, right? So 50 divided by 1,000 is what?
0.05.
So that's 0.05 dm cubed. All right. So you have the so now you have your volume, right? That's a volume that you have. Volume. All right. Let's see what else I'll go into the chat. Jada is on a roll and I love it. Jada said multiply the volume by the molar concentration to get moles. So let's see now what that would look like. Ooh. I'm writing on different color. So repeat what Jada, unmute and tell me again what you said.
To multiply the volume by the molar concentration to get the moles.
Multiply volume by molar concentration to get volume. Wait, to get volume? Because we already got volume up here, you know. Or am I like to get moles? Okay. Because I'm like, wait, what? All right. The volume is 0.05 mole volume dm cube from step one, right? And you multiply that by the molar concentration, which they gave us, and that is 0.2 moles per dm cube. And you see how the units work out nicely, guys? The dm cube cancels the dm cube here. And so you end up with, what's that number, guys? 1 point. Daniel done the problem already. And Daniel don't want to tell me how he did it. Daniel, you have to unmute and tell me step 3. So like step 2, the answer is, what's this number, guys, in moles?
Miss, I didn't get that as the answer.
What did you get as the answer? Wait, for step 2, right? We're going from, we want to calculate the mass of calcium chloride that's in this solution. That's 50,
Miss,
that's in 50 centimeters.
So help me get 0.01. What am I doing wrong?
Miss, I get 0.01 moles.
Yeah.
Okay.
Yes, that's what I got also, 0.01.
But I think Daniel is at the end, like he already got to the end and he's like finding the mass. So that's not the moles that Daniel said in the chat, guys. That's the mass. That's the final answer. Right? So don't get confused by that. Daniel gave us the mass. That's at the end. And we're at step 2, which is to find the number of moles, which is the volume times the molar concentration. So that's 0.05 dm cubed times 0.2 moles per dm cubed. And that is what? 0.01 moles, right? So then how do you get from moles to mass? Because mass is what you want at the end. Not a mass concentration, you know, a mass of calcium chloride. So how do you make that next step? That's step 3. Because that's what Daniel did that already. So his answer is that it's a mass. It's not a mole that he gave us.
Miss, you multiply the moles by the molar mass.
By the mole, yes.
Moles by molar mass. So that's moles by molar mass. So what's that? Tell me. Break it down. Tell me the numbers to multiply based on what they gave us in this problem and what we just got from step 2.
You mean hold on multiply to get the answer?
Oh, you just tell me the numbers that I need to multiply, like the actual number, the magnitude of the numbers. So mass of calcium chloride hydroxide is 111 gram per mole, right? So tell me the 2 numbers that I now need to multiply for step 3. So step 3 is going from moles to mass, right? Right, guys? So moles from step 2, we know that the moles is 0. What was the mole again? 0.01
Right.
moles. And to get to mass, you have to multiply, or is it divide?
Multiply.
Multiply by the molar mass. And then you see how this just cancel, the units cancel, and you get, what's the answer, guys?
I have 11.1.
11.1?
Yes, the answer is 1.11.
1.11. Okay, you're off by a magnitude there, I think, Aquila. But you have the right approach. I think your magnitude is just a little bit off. So what is it? 1.11 grams, right? Does everybody follow that so far? Is that
Yes, miss, I
good?
get it
Yes,
now.
miss.
Okay.
I miss have the 0, that's why.
Okay. Great, but we're all on the same page, correct? Thumbs up. I can see everybody now. So give me a thumbs up and then we'll move on to oxidation and reduction. Like, I really wanted to get to electrochemistry with you guys for these 3 classes because like electrochemistry is like hard. Like people say it's hard, students say it's hard, and it can be a little bit tricky. So I want to get to it, but we have to do oxidation and reduction first. And today's the last week. Today's the last day. So I'm just like,
Miss Lacott, last day, you're going up to 3.
ha! Who said that?
Whoever said it, I
Who
agreed. I
Who
agree.
said that? Who said that?
Miss, I can just do that for real.
All right.
Yes,
What time is
being
it
it
now?
the
2
last
o'clock.
day.
All right, we'll see what happens when we get to 2:30. Here's the deal. If you guys aren't interacting with me, I'm gonna end it at 2:30 because I'm not gonna talk to myself. Okay, that's not fun. So if you guys agree to interact with me, I can stay until 3. How does that sound?
I'll try.
Okay. All right. So let me move on to oxidation and reduction. All right. Where's my pointer? All right. All right. So we're done with this stuff then, guys. But all in all, Let me put you guys back up so I can see. Pretend that I'm seeing your beautiful faces when really I'm just like seeing the whatever your names are. But let me see. I want to see your reaction now. So we're done with mole concept. We did more concept over a 4-week period, and I really not that much time, because like each session, the first week was an hour, and then I did an hour and a half for the subsequent weeks. So before I jump into oxidation and reduction reactions and that whole thing, which is really sets the stage for electrochemistry stuff, how do you guys feel? Let me see if I can do that. Wait a little bit. Let me see something. Oh no, what did I just do? What did I just? All right, that's not gonna work right now. Oh, that's not gonna work right now. Let's not do that. Let me just stay where I am right now and ask you guys this. Stop sharing. Okay. Like, you guys probably know what I'm gonna ask. Where are you? I know there are people who joined us later, like Jamar and Jabari and a bunch of people, Daniel, Claude. I think that you guys joined us towards the end. So you joined us last week in week 3, but you've caught on pretty well, or you seem like you had like an understanding of this stuff before, because you're with us right now, right? And you're not lost, you're getting everything. So what would I say? Maybe you can unmute. Are they unmute and tell me, or you say it in the chat? Where were you at the beginning of February when we started this in your understanding of mole concept? And where are you now? You can unmute and tell me. So let's use a scale of 1 to 10. Where did you start and where are you now? So just like unmute and tell me. How about let's unmute and tell me. We're here until 3. We're a little community here. Unmute and tell me where you started and where you are, and then we can move forward. So and if there is anything that you want me to do different as we're doing this new topic today, is what I'm saying. Like, I want it to be tailored to you as much as possible. So that's why I'm asking you for your feedback right now before jumping into oxidation and reduction. So where were you on a scale of 1 to 10 when you started, and where are you now? And is there anything you want me to do different as I enter into this? Oh God, Jada said she jump off of the scale. Jada, oh gosh, you made my life. Jada said I started at 8 and now I'm at 11. Jesus, peace. Oh wow, that made my life.
My teacher didn't start to do this as yet, so.
Oh, so you
I'm
don't have a starting point then, per se, Elizabeth.
No, miss, because the teacher is doing labs now. So he said that after I finish the labs, he's going to go through this.
Oh, wait, which
with
form
us
are
through
you
the
in?
mole concept.
Which form are you in, Elizabeth?
Oh, miss, I'm actually attending evening school.
Okay, and you're doing the exam this year, right?
Yes, miss.
Okay. So you're doing labs now, and then you're gonna go to mole concept?
Yes, miss.
Okay, cool. But you're ahead, and when him start it now, you'll be like, you have it, right?
Yes, miss.
Okay. All right. So anyone else? I want to hear from as many of you as possible. So I'm gonna stop this question in like a minute or 2, but I want to know where you guys are. Jada already told me that she jump off of the scale in her understanding. 10 can hold her, she's at 11. She's at 11 right now. So who else? Okay, all right, I see that Aquila, so she doesn't really have a starting point, but she's way ahead by her estimation right now. She's way ahead. Don't have a starting point per se, but she's way ahead just over this past 3 weeks of 1.5 hours per week. I love that for you guys. Like, I love that. You see, it just takes a little bit of time, a little bit of commitment to something, and you get it, right? You get to it. Deschanel says she jumped from a 6 to 9. Deschanel, how can we get you to a 10? What is that one that's missing? How could we have gotten you to a 10? And how can we get you to a 10, or will you get yourself to a 10? What's your plan going forward?
Miss, I think that's just on my part now to practice using more questions and so forth.
Okay, that's good. Practice is always good, right? So definitely be practicing more concept type questions, and you can jump to the past papers too if you want, right? Who else? Is there anybody else that wants to talk to me before we move on? You guys not talking to me now? And that's a deal that we struck, you know, that you would talk to me. Kayla says she go from a 7 to a 10. Oh my gosh. We love to hear it. All right. Anybody else?
Miss?
Anybody? Jamar said, Miss, I had an understanding of the theory. However, the calculations always messed me up, but I'd say a 10. Okay, so you see, that's like a very solid point that Jamar just made, right? Sometimes you understand the theory, you know, meaning you know the definitions, but you haven't practiced enough or you haven't seen enough problems, and so you can't do them. So you have to keep on practicing. And I love that for this LMD and chemistry Sunday. So February we did a lot of problems, right, guys? I didn't just like teach you the things, and I taught you the definitions up front, but I also did the questions and I did them with you, and sometimes I'd ask you to do them, so that, because practice is important. Theory is good. You need to have your theory down, but you need to practice too. Okay? So
Miss?
Jamar said that, and he's a 10, so that's very good.
Sorry, Miss.
Aquila?
The challenge I'm having is that I'm working, and currently we're doing SBAs. So when the SBA demand a lot of time, you know, for you to even say, all right, let you put the SBA aside and study straightforward. It's complicated, but we're fight.
Yeah, you have to figure out how to like balance it. So that's why when I say if you have a study plan, because you can't spend all your time on any one thing, right? I don't want you to like not pay attention to the SBS, because you need to have a solid grade if you're gonna get a grade 1. But like don't sacrifice the theory don't sacrifice the theory for the SBA. Like you need to find a system that works. Come up with a study plan that you're gonna balance it. You see what I'm saying? Like I know you're working on everything, but like see if you can find a way to split the time evenly, or more time on your studies and a little bit. So maybe I don't know, what would I say? Maybe I don't want to say 75-25 split, because that's like you're like not really paying much attention. Maybe a 50-50 split. How about that? Because how much is the SBA worth from a percentage standpoint? Like when you do the breakdown, how much is the SBA worth in the grand scheme of things?
I think it's 40.
And that's how much? 40?
I'm not sure. I think it's 40.
Okay, so you use that to guide how much time you spend on it. You see what I'm saying? Like if the SBA is 40%, if the SBA
I think
is 40%,
it's 20. I think it's 20, me.
See, Aquila, you see that?
And
It's 20.
50% for the paper 2, and I believe it's 30 for paper 1.
Oh, that sounds solid. I think that's what it is. So Aquila, in light of that, do good on your SBAs, but don't spend all your time on the SBA. Like study, because all right, what we're doing here will help you a lot with the paper 1 and paper 2, and also with paper 1, because it's a conceptual understanding that we're working on. You're understanding the concepts. So when you do paper 2, you can do it. When you see paper 1 and you're choosing between different things, you know what to choose because you know the concepts. SBA is good, and you don't want to get, like, I remember when I was in high school, you know what I would do? Like, I don't know why I did this. I was like so like concerned about like doing well. Like I would like say, okay, on the worst level, if I do really poorly in my SBAs and I get like maybe 15% out of the 20, and I can like do really well on the others, on the rest of it, the other 80%, like I'd like do it like that. So like just to like kind of convince myself that I don't have to get 100% on the SBAs and I'll still be okay if I have a good conceptual understanding, because the rest of the things is 80% of the overall grade, right? So if you do really well on paper 2 and paper 1 and you get 75% out of that 80%, and on your SBAs you got like a 15%, what is that? Where are we in terms of percentage for the exam? You got a 75 out of 80% for the paper 1 and paper 2 combined, And then for the SBA, you got a 15% out of 20. Where are we from a percentage standpoint? How much is that? How much percent is that total?
It's 90.
And that's solid. What do you guys think? You don't think that's a solid number? Like, I am not advocating for not getting 100%, you know. Like, I'll be the last person to tell you to be okay with getting 90 and 95 and not 100. But what I'm saying is, when you're balancing all these things, you're balancing your personal life, your job, your other subjects, there has to be some level of like, okay, I might not obsess so much about SBAs and getting 100 on SBAs because it's not as important from a percentage standpoint. Let me focus on the conceptual understanding because that's 80%. And if I can pull off a 75 out of 80% and get a 15 out of 20% on my SBA, that's 90. That's 90 out of 100. And in anywhere you go in the world, well, in the Caribbean, from a chemistry standpoint, and you get a 90% on your CXC chemistry stuff, nobody can tell you you're on a grade 1 that. Like, I mean, I know it's like the grade is like done in relation to how everyone else does, but like a 90, like there's no way you're going to get a 90 overall and not get a grade 1. Like, do you guys see what I'm saying? Like, that's how you have to approach these things and balance it like that. Does that make sense?
Yes, miss.
Yeah, so that's what I mean. So don't spend all the time on SBA. Like, SBA is like, it's important, but don't do that, okay? Where are we now? All right, let's just move on because you guys now tell me well, I've heard from enough people and I think the general consensus is that this is good. It has helped you a lot. So let's move on to oxidation and reduction. Let's see. Let me see. All right. So oxidation and reduction reactions. So just to jump right in, there are several definitions of oxidation that is good for you to know. So we're gonna like go through them I'm not gonna spend too much time on it because I'm also assuming that you guys have done it to a certain extent already.
No, miss.
You haven't done it as yet?
No, miss.
Oh, okay. There are a bunch of different definitions, but like I think the most important definition for oxidation and reduction is in terms of electron transfer and what happens to electrons, right? But we're gonna go through the other definitions like real quick so you can see it in your head, right? So let's see. Oxidation. So I'm defining this definition on this slide is in terms of molecular oxygen and what happens from molecular oxygen standpoint, but I'm also gonna like, I might combine, compare and contrast it with other definitions so you guys can see, right? So typically from a molecular oxygen standpoint, so by that I mean the oxygen molecule standpoint, oxidation is often defined as when a compound gains an oxygen, right? A molecule of oxygen. So it gains a molecular oxygen, and we will say that that compound was oxidized, right? So let me write that real quick. So gain of oxygen, right? And by that same, oh Lord, ooh, no, that didn't write. Let me misspell the oxygen for oxygen. So a gain of oxygen is what we say oxidation. And guys, it makes sense, right? From the way the word sounds standpoint, oxidation, you're adding oxygen to the thing, right? And then by that same token, what would you deduce that reduction might be from an oxygen standpoint? What's reduction?
The loss of oxygen molecules.
The loss of oxygen molecules. That's exactly right there, Chanel. So let me just write that real quick. And then also another definition that I'll just add in right here is like a definition from hydrogen, from a hydrogen standpoint as well. Maybe I won't say, I'm not going to tell you guys that to distract you here. But reduction, as Chanel said, would be a loss of oxygen, and it can also be a gain of hydrogen. right? For reduction. So I'm not gonna focus on it though, because I don't want to like confuse you guys, but that is a definition as well from a hydrogen standpoint. But let's just focus on oxygen and then electron transfer. So reduction, as Deschanel said, is a loss of hydrogen. So it gets reduced. If it loses hydrogen, we say reduced, right? And then I'll just like show you an example. And then you look at this and tell me what was oxidized and tell me what was reduced from this. Oh, and let me just add that the two things happen simultaneously, right? So like, if you see an equation like this, the reason why it's called oxidation reduction reaction is because oxidation and reduction happen simultaneously. So something gets oxidized, something gets reduced. Something gets oxidized, something gets reduced, right? It's like that. So looking at this equation right here, tell me what was oxidized and what was reduced. So when you look at it over here and you look at it over here, what change happened from an oxidation or reduction standpoint, given these definitions that I just gave you?
Not sure. Let me try.
The copper oxide was reduced, miss.
Copper, okay, copper
hydrogen.
oxide was reduced. Wait, so let me see. Who said copper oxide was reduced?
Me, miss. Jabari.
Who, Jabari? Okay, so Jabari said copper oxide was reduced because it lost that oxygen that it had on the left. And when you look at it on the right, now it's by itself, right? The copper is by itself. So the copper oxide was reduced, okay. And then what happened to the hydrogen? Jada says it was oxidized. It gained oxygen, right, Aquila? So the hydrogen was oxidized. So you guys see that definition, fairly straightforward, right? You're just looking at what happens from an oxidation standpoint. Did it gain oxygen or did it lose oxygen? However, you might realize that this definition kind of falls apart if you have an equation in which there's no oxygen. And you guys might be very well aware that there are all these classes of equations in chemistry. And even some of the equations that we looked at when we were doing mole concept, they had no oxygen in them, right? It wasn't an oxygen containing compound that was reacting with another one. It was just, so say magnesium and chlorine, that's gonna actually be our next example, right? But say you have a magnesium and a chlorine reacting, there is no oxygen in it. It's magnesium and chlorine. So then if you, the student, are supposed to be able to deduce what was oxidized and what was reduced, you're not going to know what to do if this is the only definition that you had. Do you see what I'm saying?
Yes, miss.
Yes,
So there
miss.
have to be other definitions, and what I think is the most important definition is this next one that's coming up, which is written, right, in terms of electron transfer, right? So this is a definition in terms of electron transfer. And what do I mean by electron transfer, guys? Well, I gave you the first answer. So what do I mean by electron transfer?
Losing and gaining of an electron.
Exactly, and that's like what's that? Is that Jabari?
No,
Or is that Claude? Claude, when going back to basics, right? What do we call it when compounds are formed as a result of a loss of electrons or gain of electrons? What kind of bonding is that typically indicative of?
It's ionic bonding, miss.
Exactly. So that would be ionic bonding, right? So, you know, ionic bonding is a transfer of electrons. So you have typically those elements on your left-hand side of the periodic table, your metals, right? They lose their valence electrons. And then the non-metals on the far right, so say your halogens, like what's the mnemonic? Florence can bring ice, right? So let me write that down. Florence can bring ice. That's your group 7 stuff, your group 7 elements. So you would do, let me just, where can I put this? Let me put it over here. Can you guys see? F, Florence can bring ice. So that's fluorine, chlorine, bromine, iodine. That's the first four elements in group 7. And these typically form these ions, right? Well, this is Br, bromine. They typically form ions, they typically gain an electron, right? And you typically have your metals losing the electrons, your group 1 metals or your group 2 metals losing their electrons to these halogens, right, that are in group 7. So that directly is a transfer of electrons, right, from your metal to your non-metal. Your metals typically lose their electron, their outermost shell, and the non-metals just grab them. So it's a transfer of electrons, right? And so bringing it back to this, what we're saying is that oxidation is a loss of electrons. So if you have a compound and it loses electrons, it doesn't even have to be from a, well, it's often from an ionic bonding standpoint, but you'll see what I mean. Like you look at it in the equation, the grand scheme of things, and it's an oxidation if it's a loss of electrons. It's largely for ionic compounds, so that's essentially what happens to ionic compounds. But oxidation would then be a loss of electrons, right? So are we all clear? Are we on the same page with that stuff? And just kind of like bringing it back to bonding and ionic bonding, so you guys can see how that comes into play here. Are we clear on that?
Yes, miss.
Yes.
Okay. Oh yeah. Yes, Jada, I forgot the L for chlorine. I don't know what I was doing right there. But it's fluorines can bring ice. Fluorine, chlorine, bromine, iodine. And that's how they go down the group, right? Okay, so oxidation is a loss of electrons, right? And you typically say oil, right? Remember oil rig? Do you know that mnemonic? Well, if you haven't learned this as yet, you probably don't know about oil rig. But oil rig is a way of remembering what oxidation does from an electron transfer standpoint and what reduction does from an electron transfer standpoint. So I'm going to show you, yeah, oxidation is loss, reduction is gain. Yes, Jada, that's exactly right. So let me show you that. So you see that oil? It means oxidation is loss. It's a loss of electrons, right? And so reduction is then the opposite of oxidation, right? Opposite. So whatever one is, the other one is the opposite. So oxidation is loss, then reduction is gain. It's a gain of electrons. So you guys see that? So that's just a shorthand way of remembering it. Oil rig, right? Are you guys clear with that? It's just definitions,
Yes,
right?
Yes, miss.
Hold
Okay.
on, miss, hold on, wait there. So earlier when you said a compound that is gain molecule of oxygen, you didn't say that's oxidation?
That's oxidation, yeah.
So the reduction is the compound loses molecule of oxygen?
Yeah, that's exactly right. So that's the definition from an oxygen standpoint. Yeah, that's right. And so now we're defining it in terms of electrons and how electrons transfer. And so we're saying that oxidation then is when if me and you stand up beside each other, Aquila, that this is how it typically works. It happens in tandem, right? Aquila and Nyla are standing next to each other. I lose an electron, you gain an electron. If I lose it, I was oxidized. And you gaining it means that you were reduced. Does that make sense? But it's happening
miss,
together.
clear.
I'm oxidized, I lose an electron. You are reduced because you take my electron. You've gained my electron. So you are reduced. Does that make sense?
Yes, miss.
So like I'm throwing something at you. What should I throw at you? I'm throwing this at you. And by me throwing this to you, this is my electron. You take it, you reduced, and I'm oxidized because I've lost it now that you've taken it. You see what I'm saying?
Yes, miss.
Like that. So that's this transfer part, this electron transfer part of it. So then if we look at this, Mg, it's a solid. Wait, nope, not yet. So Mg is a solid. You have chlorine is a gas. And so from that, you get magnesium chloride. And as we said earlier, I think it was Claude or Gemma or Jabari was saying ionic bonding, something along those lines. This is an example of ionic bonding. And you can see based on what I was saying earlier, for the electron transfer definition, you need it. Because like if you only had this, if you had this equation and you're looking at it and I said, Aquila, tell me what was oxidized and tell me what was reduced, you wouldn't be able to because there is no oxygen in it. So you can't tell me from an oxygen standpoint what lost oxygen and what gained oxygen because there are no oxygens in the equation, period. You see what I'm saying? So when you see this kind of an equation, your analysis has to be an electron transfer analysis, right? So, okay, I haven't thought you guys about oxidation numbers, but it's gonna be at the end of this. So I'm gonna kind of jump ahead when I'm describing what's happening here to you. But when you have like an element by itself or an atom of an element that's like by itself, they'll call it the free state. So it's like free, it's not bonded with anything. It's just how you would find it in nature. The oxidation state or the oxidation number, which is the number that defines what state is it, the degree of oxidation or reduction of that atom. The oxidation number for an atom or an element that's not bonded to anything else, it can be bonded to itself, but it's not bonded to anything else, is 0. 0, right? So, let me write that. All right, so Kayla says 0, good. So you guys are familiar with that. Mg was oxidized, what Jada is saying, but let me just walk through it and just show everybody how they can see what happened from an electron transfer standpoint when you're in a, when you have an equation like this, right? All right. So as I said, when you have an element that's unbonded, it can be bonded to itself, but it can't be bonded to anything else. If it's in that state, the oxidation number, which defines the degree of whether it's oxidized or reduced, is gonna be 0, right? So this oxidation number, I'm gonna write them up here. For magnesium is 0, and for chlorine is 0, because they're by themselves, they're not bonded yet. But when they go over here, the oxidation number is gonna change, right? And so for magnesium, because magnesium is in group 2, and it has 2 valence electrons, because it's in group 2, right? All the group 2 metals have 2 electrons in their outermost shell. Those 2 electrons, they're gonna lose whenever they're like bonding and they're doing this ionic bonding stuff. So because magnesium is gonna lose 2 electrons to combine with this, it's gonna be what? Mg2 plus ion is what would be formed, and the oxidation number would just be +2. And then chlorine is in group 7, as I said, and it needs to gain 1. So the oxidation number would be -1 for chlorine, right? Just keep that in mind for now. Just keep that where it is right now in your mind. I'm gonna go back now and show you the electron transfer stuff, the equation for the electron transfer. So you can see, so all right. So when you get to electrochemistry, and you're gonna have to write half equations to say what happened at the cathode reduction takes place, and the anode oxidation takes place. So they're gonna ask you to write the equation for what happens in each case. So essentially, they're gonna ask you to show me the equation that you used to know that that is oxidized. Show me the equation that you used to know that that was reduced. And so that's kind of what I'm gonna write now from an electron transfer standpoint, right? All right, so up here, we already established that we have magnesium by itself, right? And magnesium, as we said, it is important for you guys to know, right? That's why they build the syllabus like that. It build up. So you build on, you do periodic table and periodicity, and then you do ionic bonding, and then you do mole concept, and then you do this oxidation stuff because it's building on your knowledge, right? So magnesium is in group 2. So that means that it has 2 valence electrons. So it has 2 electrons in its outermost shell that when it's combining with another element that's like a non-metal, like chlorine, like this, it's gonna want to lose those 2, right? So remember we say oxidation is loss. So oxidation is loss, and so Mg will lose 2 from this basis that it has 2 valence electrons. It needs to lose the 2 so it can look like the nearest noble gas and become a stable atom, right? So that's what it wants to do. It wants to just give away those 2 so it can become stable and nice. So we'll give away those 2, right? So we're starting with magnesium here in its free state, where the oxidation number is 0, and then it's gonna give up those 2 electrons. It's gonna lose those 2 electrons. And the way that we write that is we have this arrow going over here, and we show our 2 electrons that it lost. But we have to have, going back to our balanced equations, we have to have a balance here. So we have to have our magnesium over here too, right? But we have to also show the oxidation state, or show that plus 2 then, right? Or so it will be 2 plus. Guys, don't worry about the 2 plus versus plus 2. Like, I know that they teach you to say it's 2 plus when it's like you're doing ionic bonding, and when it's oxidation state, you put the plus before the 2. But like, don't worry about that because it can get confusing. As long as you know what the magnitude of the charge is, that should be okay, right? So the magnesium in the free state over here is getting oxidized because it's losing its 2 valence electrons. So it loses the 2, and now you have Mg2 plus, like I wrote up here, right? And so you can see that the balance, the charge, the magnesium is balanced on both sides. You have 1 magnesium here, and you have 1 magnesium here, and the charge is also balanced because you have 2 electrons which are negatively charged plus this 2 plus. So when you add them together, you get 0. So do you guys see that? Are you guys clear on all of this stuff? That's just for the oxidation part, you know. I have to show you the reduction part, but that's just for the oxidation part, which is magnesium that's oxidized because it's losing 2 electrons. So is that clear to you guys?
Yes, miss.
Yes, miss.
Okay. Okay, great. So then, all right, so that's oxidation. Now let me show you the reduction one. And so guys, if magnesium was oxidized, what happened to chlorine?
It's reduced.
Reduced.
It's reduced. I'm gonna show you what that looks like, okay? Like how you'd write that half equation. They call these things half equation because what happened to one half, then what happened to the other half. So it's like half equations, right? So you see that? That's exactly what I just showed you guys. The Mg goes to Mg2 plus 2E, right? So we're all on the same page on that, right? Do you guys see that, how that works? All right.
Yes.
Okay.
Yes, miss.
Great. Okay. Oh, I gave away the answer. I shouldn't have done that. Anyways, I want to show you guys for chlorine now, okay? So let me clear this screen. All right, so I'm going to do a similar analysis for chlorine, right? So as I said, chlorine is in group 7, right? So it's Cl is, chlorine is in group 7. It has 7 valence electrons. So it needs to gain how many, guys, to be satisfied? To be like its nearest noble. So it needs to gain 1, right? Yeah. So it needs to gain 1. It needs to gain 1 electron. And what did you say reduction is again?
The gain in
It
electrons.
gains electrons.
Okay. So look at this now. So chlorine needs to gain 1. And reduction is gain, right? So then, okay, I'm kind of writing all over the place, but you guys just follow me. Just follow me here. I'm gonna write it here. So we have Cl2 here. It's in its free state, so its oxidation number is 0, right? It's gonna gain. So let's just show it gaining 2. It's gonna gain 2 electrons because that's what magnesium lost. Magnesium lost 2, so chlorine has 2 to gain. And because we have 2 chlorine atoms, they each take 1. Each of them need 1 from down here. From down here, we say each chlorine atom needs to gain 1, but we have 2 to give it because magnesium is losing 2. And additionally, a chlorine molecule is made up of 2 chlorine atoms. So each of them going to take 1. Does that make sense?
Yes, miss.
Miss, repeat, miss.
Okay. So magnesium is the pair, right? Magnesium is what's being oxidized so that chlorine can be reduced, right? So because magnesium lost 2, needs to lose 2, that's what happens when it's oxidized. That means that the chlorine molecule needs to take those 2, right? But a chlorine molecule is made up of 2 atoms of chlorine, as you see in this equation, Cl2. So there are 2 chlorine atoms, right? Magnesium is giving away 2, but we said from the bottom that each chlorine atom only needs 1. But because we have 2, then the overall system is gonna take 2. Does that make sense? Because in the overall system, there are 2 chlorine atoms that make up that chlorine molecule, but on an individual level, each chlorine atom only needs 1 electron because it has 7 in the outermost shell, and it needs to gain 1 to get to 8 and be satisfied. Does that make sense?
Yep,
Yes,
I
miss.
understand.
Okay, so then now on the right-hand side, what's supposed to be on my right-hand side, guys? So we're balancing both the charge and the element. So from a chlorine perspective, what should be on the right-hand side of that equation that I just wrote? We're balancing charge and atoms. Remember that now. So yeah, on the left-hand side, we're saying that we're in the free state, the chlorine is 0 and it's gaining 2 electrons. So the charge on the right-hand side will have to be overall minus 2, right? Because the left-hand side is minus 2 now. And so the right-hand side has to be the same, minus 2. Do you guys see that? Cl0. So essentially what we're doing is 0 plus negative 2. So that's minus 2. And then on the right-hand side, now we're getting our chlorine ion because it's an ionic bonding that happens between magnesium and chlorine. So where's my thing? Where's my
So you're saying that even though chlorine is -1, they want, but magnesium might give it 2. So basically the whole 2 you're gonna get.
Exactly.
That's what you're saying.
Yeah, and you're going to just split it between 2 of you. Well, yeah, you need 2 chlorine to take those 2 essentially, and conveniently, the chlorine molecule is made up of 2 atoms. You see what I'm saying? It's like, think of it this way, and this is like a neat way to teach ionic bonding. This is kind of how I teach it with my students who are in 4th form, and I'm teaching them on a one-on-one level. The way I teach them is like, I'm saying that if I have 2, all right, so I'm Nyla, and I'm giving away 2, may I give away 2 bag juice? 2 bag juice. I'm giving away 2 bag juices, but you, Aquila, you don't want to be too greedy. You're only one person. You can only take 1. So then you go and get a friend of yours that is very similar like you, which maybe she's just like you. Maybe it's your twin. Let's say you're a twin. It's your twin sister, and she likes bag juice too. You don't want to be too greedy because you only need 1 of the bag juice, but I'm giving away 2. So you get your twin sister and she takes 1 and you take 1. I'm satisfied, you're both satisfied. Does that make sense?
Yes, please.
So that's kind of how I teach ionic bonding, from the standpoint of when you see something like this where you're like, oh, magnesium is +2, it's giving away 2, but chlorine only needs 1. because chlorine is in group 7, so it can only take one. Well, there are going to be 2 chlorines then, because one chlorine only need 1. It can't take the 2, but I'm giving away 2. So what you're going to do is find a friend who's just like you, only need 1 as well, and then they'll take 1, and so everybody's satisfied. So that's kind of what happens here. Does that make sense? So let me balance it from, let me balance charge and atoms, because right now it's not balanced the way I've written it. The way I've written it, where's my thing? Okay, the way I've written it, I need to put 2 here, right? So you have 2 chlorine atoms on the right, and you have 2 chlorine atoms on the left. As I said, the overall charge on the left is going to be 0 plus -2, so it's -2. That's the overall charge on the left. And then on the right, it's this 2 that's before the chlorine times that -1 up top. So the overall charge on the right is also -2. So we have 2 chlorine atoms on the left. We have 2 chlorine atoms on the right. We have a -2 charge on the left, and we have a -2 charge on the right. So our charge is balanced and our atoms are balanced. So now we have 2 half equations here. And when you combine them, that's exactly what you get. You get that top one. That Mg solid plus Cl2 plus goes to MgCl2 solid. Does that make sense to you guys? If there's any question on that, just let me know. Just stop me right here and let me know. Is that clear, guys? Oxidation.
Clear.
Clear?
Yes, miss, clear.
Okay, this is like the basis, the fundamental stuff. And like those of you who have done electrochemistry, you see this equation in electrochemistry, like this kind of way that you write an equation?
Yes, miss.
Yes, miss.
Yeah, so this is where it comes from, right? This idea of oxidation and reduction. So this is like, I think that this is the best definition of oxidation and reduction, because from an electron standpoint, you can always see what's happening with an electron. If it's like, if the electrons are lost and if they're gained, and then, you know, oxidation is lost, oil, and the reduction is gained, so that's rig, right? Okay. So let me clear this and move on to my next slide. What time is it? Oh Lord, 15 minutes. We're not doing too bad. Okay, so that's what we wrote, right? So you see, guys, that's the breakdown. Those are what we call half equations. So let me just write that real quick. These are what we call half. So like, guys, I'm kind of like sneaking in some electrochemistry here. I don't know if you realize, because this is like electrochemistry concept. So this would be oxidation, that's a loss of electrons. And then this is reduction, which is a gain of electrons. Because you see it start from 0 and then it gain 1 to become negative, right? Each of them gain 1 and then they start from 0 and then it goes to +2. So then it loses, right? Because like you go 0 and you go to +2. +2 is because it loses 2 electrons. So this is the top one is oxidation, the bottom one is reduction. And then while I'm on this slide, it kind of leads to the next slide, right? But like you guys see how for the magnesium, you go from 0 to +2. So it becomes more positive, or it increases. The number, the oxidation number increases. So that's also a definition of oxidation. It's a case in which you have an increase in oxidation state. So you go from 0 to +2, that's an increase, right? And for here, you're going from 0 to, well, it's really -1 on an individual level, but because there are 2 of them, it ends up being total -2, right? But the oxidation number itself is going from 0 to -1. Do you guys see that? It's 0 to -1 because you have 2. The overall charge balance is -2. Do you guys see that? Just let me know. So we're all on the same page in terms of what the oxidation number is. It's -1, right? That's clear?
Yes, miss.
Okay. So then now what I'm saying is it's another definition of oxidation and reduction is that oxidation is an increase in the oxidation number and reduction is a decrease in the oxidation number. So here you're going from 0 to -1. You see that? Where's my pen? Okay. So this is a decrease. Decrease. The oxidation number decreases, right? So you guys see that? So now you have three definitions of oxidation and reduction you have three definitions now, right? You have one, oxidation is a gain of oxygen, reduction is a loss of oxygen. Oxidation is a loss of electrons and reduction is a gain of electrons. Oxidation is an increase in the oxidation number, so you're going from 0 to +2, and reduction is a decrease or a reduction in the oxidation number. So here you're going from 0 to -1, right? So that's three definitions for you guys now. Are you guys clear on the concept now? Like more or less?
Yes, miss.
Okay. Okay. Whew. All right. So when we talk about oxidation numbers or oxidation states, we do that a lot of times to like account for covalent compounds. So like water, like water is a covalent compound. So let me show you. So like water, that's a covalent compound. You can speak of an ionic. You can't really speak of this in an ionic way. Like just now, when I did that whole example that I did, I was doing, it was basically ionic bonding I was showing you guys in terms of oxidation and reduction, right? But when it's like water, that's like a covalent compound, you can't really analyze it that way. And so you typically speak of an oxidation number, oxidation state exclusively when it comes to covalent compound. That's the only way you can really define if a covalent compound's outside of the oxygen thing, right? So you're applying these oxidation numbers to covalent compounds. And so as I mentioned before, the oxidation number is the number that we give to atom or ion in a compound to show the extent to which that atom is oxidized or reduced, right? And sometimes it's given along with the formula. So like if you say copper 2 oxide, guys, what's the oxidation number of copper in copper 2 oxide? Because they're essentially, I just told you what it is. It's copper 2 oxide. So what's the oxidation number of copper in copper 2 oxide?
2, miss.
It's 2, right? So it's +2. They basically told you that. So like, just keep that in mind, that when you see like these formulas and they give you these Roman numerals in parentheses, that's typically what the oxidation number is. And they do that a lot for like transition metals. So for like iron, you will see like iron 2 oxide. We did a problem with an iron 2 oxide, I think, when we were doing Molar concept. So you see like iron 2 oxide or iron 3 oxide, and that just means that that's the oxidation state, right? Or the oxidation number. So are we clear on that? So that's this concept or this idea of an oxidation number. That's what that means. It's a number that tells you how oxidized the compound is. You can use them when you're dealing with covalent compounds because you can't do an ionic analysis. So you have to use your oxidation numbers. And then we have cases in which we have given them to you in the formula, like copper 2 oxide. You know right away by looking here that the oxidation number, the oxidation state is 2, right? So we're all clear on that, because now I'm going to jump into some rules that you need to remember when you're determining oxidation states, or just, determining oxidation states or determining what happened, was something oxidized or reduced. So if we're all clear on this slide, just give me a thumbs up and I'll move to my next slide, which is just like rules. Okay, so I see 1 thumbs up. Are there any more? Or are you guys sleeping? I see more, I see more, I see more. All right. Okay. I see all those thumbs up now, so we can move on. All right, so let's move on to these rules and then we are done. All right, let me clear these. All right, so let's move to these rules, clear all these drawings. All right, so I'm just gonna walk you through these rules, guys, which honestly, I think this is a solid place to stop. So rules for assigning. So you're assigning oxidation numbers and oxidation state, because that's what I did. When we were just doing magnesium and chlorine, I assigned them based on these rules that I know, that I'm now teaching you, so that you know and you'll be able to assign oxidation numbers and oxidation states, right? So the first one is exactly what I told you before, where the oxidation number, which is this oxno, oxidation number of all atoms of an element in its free state is 0. And what did I mean by free state again? I told you guys earlier, when it's in its free state, what does that mean?
When it's not bonding with anything.
Exactly.
Right,
So when it's by itself, it's not bonded with anything. Or maybe it's bonded to itself, like chlorine, because you have Cl2, and oxygen, you have O2, right? But outside of that, you just have like an Mg or a C or Mg or potassium or K or anything that's by itself, not bonded, is in its free state, the oxidation number is 0. And that's the first rule. So just remember, that's easy. Always remember that. And then the second one is that the oxidation number of an ion arising from a single atom is equal to the charge on the ion. So like, look at this now. So that's where the charge is coming, and that's what I used before when I was telling you that you have, let me use this again. So like magnesium, all right, magnesium is a single atom. And when it's in an ionic form, it's Mg2+, right? So you see this charge? That is the oxidation number. You guys see that?
Yes, miss.
Yes, miss.
And then similarly for chlorine, you have your chlorine in its free state. It's like this diatomic molecule, it's 0. And then when it's like ionized, as I said, like we go to 2Cl, like remember the example I was doing with Aquila where I said she's gonna have to bring her twin, so I need 2 of them, but each of them are only taking 1. So the charge on the ion is -1. That's the oxidation number. That's that -1. That's the charge on the ion. So that's the oxidation number. Guys, do you guys see that now?
Yes, miss.
So that's
Yes,
what that rule there means. So then let me clear that. The oxidation number. So guys, pay attention to this one, because this is where it kind of starts to get trickier. The oxidation number of an oxygen atom in a compound is -2, but in peroxides, it's -1. So you have to remember that. So let me show you what's an oxygen containing compound? Water, right? Let's look at water. So water is H2O, and in water, the oxidation number of the oxygen atom is gonna be -2, right? But when it's in a peroxide, so you know you have hydrogen peroxide, which all of us have in our bathrooms, right? Hydrogen peroxide, when it's like this, it's -1. And what brilliant student can tell me why it's -1 when it's a peroxide? Does anybody know why? Like why it would be -1 there, but -2 here?
It's because it's shared between 2 oxygen.
Exact. That's exactly right. Who said that? That's exactly right.
Jawari, Miss Jawari.
Jabari. Okay. Okay, so that's exactly right. Okay. So let me move on to my other rule. Okay, so the oxidation number of a hydrogen atom in a compound is +1, but when it is combined with a metal alone, it's -1. So let me show you an example. So hydrogen in a compound, let's use water again. So H2O, oxygen by itself, that's here. It's -2 for oxygen. And then for hydrogen, we're saying it's +1, right? So you see, 2 times plus 1 is plus 2, and then this minus 2, so it'll be 2 minus 2. Well, this is another rule. Let me not jump the gun, but just keep that in mind. The hydrogen here is plus 1. The oxygen is minus 2. But like if we have hydrogen combined with a metal alone, so like if we have sodium is a metal, and we have the hydrogen here, that's sodium hydride, that's what we'd call a hydride. Then, because the sodium is plus, because it's going to give up 1, it's in group 1, it has 1 in the outermost shell, then this will have to gain 1. So it will just be minus 1. So it's minus 1 when it's combined with a metal alone. And then when it's in like a compound form, like water, it's plus 1. Do you guys see that? So it's plus 1 here in a compound form, and then it's minus 1 when it's with a metal alone. Does that make sense?
Yes, miss.
Yes, miss.
Hold on,
Okay.
miss, you can go over back that for me, please.
Okay, so for the first part, it says the oxidation number. Let me get my mouse. Let me get my pointer so I can point at it. Okay. Okay, yeah. So when the hydrogen atom is in a compound like water, like H2O like this, you already know from the rule number 3 that the oxygen is minus 2, right? And they're telling us that when you have hydrogen in a compound like this, the oxidation number is plus 1. So it's plus 1 here. And then when it's like with a metal alone, like sodium, it will be like minus 1. And then the sodium is plus 1 because a similar analysis that we did for magnesium, where sodium is in group 1, it has to lose 1 to become stable. So this will be plus 1 and this will be minus 1. Does that make sense? That's what the rule is saying. Does that make sense, Aquila?
I still not get it.
Oh, so they're telling us what it is, right? They're telling us that when it's in like water or like a compound, when it's in a compound, right? Like water is a compound, H2O, then one of this hydrogen, the oxidation number is gonna be plus 1. So they're telling us what it's gonna be. And when it's like with a metal alone, like sodium, so you have sodium hydride, then in this case, the oxidation number will be minus 1. Do you see what I mean? No?
Yes, miss.
Okay. All right, so then, okay, so then rule 5 says, and this is kind of where I was kind of trying to jump the gun with you guys, but I'll just do it here. The sum of all oxidation numbers of the atoms or ions in a compound is 0. So let me show you, starting back from our first example. Okay, Akila, thanks for coming. Thanks for coming. Okay, so let me just show you real quick. So, all right, so our first example, let me show you MgCl2, right? The oxidation number of the chlorine is minus 1, right? And the oxidation number of the magnesium is plus 2, right? So if we add up all of them, so for magnesium is plus 2, and then for chlorine is minus 1, but we have 2 chlorines, so it's gonna be minus 2 total, right? So that's like plus 2 plus minus 2. What is that, guys? 0.
0.
So that's what they mean, 0. And if I show you for like a covalent compound like water, it's like this, H2O. Following our rules, we know that the oxidation number for oxygen, when it's in like a compound like that, it's minus 2. And hydrogen is plus 1. That's what our rules just told us, right? So we have 2 of them there. So it's 2 times plus 1 plus, we have one oxygen, so it's just 1 times minus 2. So you see we have plus 2 minus 2 is equal to 0. You see that?
Yes, miss.
So that's what that rule means. And then now the final rule is dun, 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 the sum of all oxidation numbers in a compound ion or radical is equal to the charge on the radical or compound ion. Like that's a lot, and I'll just show you what that means. So let's use a compound ion that I think for the most part we're all familiar with, or we've at least seen once, and that's a sulfate ion. So let me do it for the sulfate ion, which is SO4. You said 2. Where did my thing go? SO4 2 minus, right? The charge on the radical or compound ion is a compound ion, right? The charge on this compound ion is -2 or 2 minus, right? So every single thing needs to add up to that -2. All of the oxidation numbers of these ions have to add up to the charge on the ion, which is -2, right? And so what that might look like, let me just show you a typical question that you might get on something like this. So like, okay. So what a question like this might look like, or the testing you on this rule is you have SO4. So is SO4 2 minus for the sulfate, right? Yes. So that's what it is for the sulfate. So then the charge on this radical, on this compound ion or radical, they call it, is this. It's -2. It's that thing up top. So it's -2 total charge, right? So if I want to know what is the oxidation state of sulfur, because we know what oxygen is already, right? They already told us in the rules that it's going to be -2. So I already know what the charge is for oxygen. It's -2, but I don't know what it is for sulfur. So if I want to find out sulfur, let me call it oxidation number X, right? I would say X plus 4, because there are 4 oxygens, 4 times the oxidation number of oxygen in this state is -2, right? That would be equal to this, which is the total charge on the radical, which is -2. So that's this. So then if I want to find the oxidation number of X, I would say X is equal to -2. And then this is what? So this is X plus X plus -8 is equal to -2. So X is going to be equal to -2 plus 8, right? Because I'm bringing it over the equal sign. So this sign is going to flip and it's going to become +8. So then the oxidation state of sulfur, which is X, is going to be
6.
dun, 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 +6. I'm going to give you one problem and then we're going to be done. I'm going to give somebody this to do. So find it for this for me. Find it for... And then I'll know that, yeah, you have this, you understand that, and then, yeah, we're good. We are good here. I'm going to give you to calculate it for the chromate ion. That's very common. We use that potassium dichromate a lot to test if something was oxidized or reduced. So I'm going to give you that to do so you can see what that looks like. So it's Cr2O72 minus ion. And I want you guys to find out what is this. What is chromate? Chromate is X. So you're finding what is for one chromate, like what's the oxidation state of chromium is what it is in this compound ion. You guys, you get what I'm asking you to do? Okay, any takers?
Yes, miss.
Wow, that was fast. Jada and Daniel already say a 6. How do you guys find that so quick? Tell me. How do you know it's 6 so quick?
Miss, what I have 2x because it's 2 chromium. I have 2x plus 7 in brackets -2 equal to the total charge, which is 2 minus.
Yes, and that gives you a 6, right?
Yes, miss.
All right. Thank you so much for that, Daniel. That was so quick. Thank you so much for that. And with that, guys, we are done. We are done. Oh, wow. Guys, Britannia. Okay, Britannia says, explain it again. Let me explain that. Let me write it out. Okay. So Britannia, what we're saying is that there are 2 chromiums, right? So it's 2 times X plus there are 7 oxygens. So 7 times what we know the oxidation state of oxygen to be in a compound is -2. So it's 7 times -2, and that's going to be equal to the charge on the overall ion, which is -2 from here. We get that from here, right? So then when we solve this algebraically, we're going to get 2x is equal to -2 plus 14. So that 2x is going to be equal to plus 12. And then, so since 2x is equal to plus 12, then one so 1 chromium, the oxidation number of 1 chromium is going to be plus 6. Does that make sense, Britannia? Does that make sense, Britannia? Do you see that? Okay, I see that thumbs up. Okay, great. All right, guys, it's 3:10. We are done. So we're done with the month of February. We're done with the free, well, I mean, we're done with the free stuff. We've done 4 weeks of this. We did more concept and we did a little bit of acid base because I wanted to show you guys titration. And then now we did like a high level overview of oxidation and reduction. So you have like the basics that you need to know for oxidation and reduction. And then electrochemistry, you can put the pieces together on that foundation that we built today from an oxidation standpoint. So going forward, as I said, like I have a vested interest in you guys succeeding. So like I don't feel right just like ditching you guys from here on out, right? So I'm not what I can say is that I'm not gonna do every week going forward for Sunday, but I could do maybe 2 Sundays out of March, and we do this same thing. But I want you guys to tell me what topics you would want me to cover. That's for March. We're talking about March now. I'd probably do 2 Sundays out of March. So write in the chat what topic you would want me to cover, and I will take what most people want, and I'll do that 1 Sunday, and then the other Sunday with the other one. And then for April, I'll do some past paper questions, some marathons, but those are gonna be paid, guys. Okay. So February free, March free.
What would be the cost for the past papers?
I'm still deciding. So depending on how long I'm gonna do it and everything that I'm gonna give you in the package, I'm gonna decide what the price is. Okay. for that, but
Okay,
that would be for April. Yeah, that would be for April. And then for March, I would do 2 Sundays in March. Just as how we've done for February, 2 Sundays in March. And then April, I'll probably like pick a weekend or 2 like for a marathon session. So like maybe all day, just pass papers, and then you guys should be good. But like I don't feel good just like leaving you guys now. Like just being like, okay, guys, we're done. February was free, we're done. Like I feel bad. I just feel bad. So I'll do like 2 Sundays in March and then paid past paper marathons in April. Okay? Does that sound fair to you guys?
Yes, miss.
Okay. So then of course I have one-on-one tutoring that's paid, right? That you can do whenever you want. So just like message me and tell me if you want to do a one-on-one tutoring session. I'm gonna put my price in the chat, and I can give you a discount because you're from the chemistry Sundays, free chemistry Sundays. But like my rate is this. I'm putting it in the chat right now. So it's like oh well, wait, no. So this is the breakdown of my one-on-one sessions. So that's kind of what I have planned going forward. So okay, so yeah, so that's my rate for one-on-one tutoring. So you can do that too if you want one-on-one help, because I'll only be online 2 Sundays out of March, and then in April is just like past paper marathons, right? So I'm not gonna be teaching as I did for February. So like if you want to capitalize on the one-on-one sessions, those are my rates in the chat. But then going forward, we'll probably do March 13 and March 27, right? For March, let me write it in the chat too. Those Sundays, March 13th and March 27th for like topics. So guys, you have time. Like I'm giving you a week to figure out what you want me to teach you on the 13th and then on the 27th. But you can just drop in the chat right now if you know off the top of your head what topics you would want to see. Okay, so Jada said electrolysis. That's a natural extension of what we did today. So that would be a nice one, right? So guys, Jabari, Jamar, Daniel, Elizabeth, Claude, who else is there? Janelle, Deschanel, Kaylee, Aquila, Britannia, Kaylia, Paige. Drop in the chat what topics you think off the top of your head you'd want to see for those 2 Sundays in March, and let me just see. And then yeah, and then yeah, so that's kind of where we are now. But I don't want to be like, hi guys, February was great, bye. I don't want to do that. Like I feel like I have to keep going, you know, to a certain extent. So that's kind of what I'm offering. That's what I have. I have the one-on-one sessions, and then I'll have 2 classes in March, and then marathons in April. Those are paid marathons. We'll go through Intel information as well. So like that would be a nice package for you. Obviously, it's not going to be expensive because I know that you guys aren't working. So I won't like charge a lot, but like it's gonna be a little fee because it's a lot more involved than what we've been doing here, right? It's gonna be a lot more involved than what we've been doing here for these lectures. I am looking for something. I'm looking for something to put in the chat. Well, hopefully you guys are following us on Instagram, so you'll see whatever updates there are there. So you'll see those updates there. But as I said right now, March 13, March 27, I'll do this again, what I'm doing right now, free. And then April is when you start paying for like past paper marathons, which I think that's reasonable. in my estimation. So that's kind of where we are. Thank you guys for coming and for being so attentive and participating. And I see a lot of you guys say that it has helped you tremendously. And I'm so, so happy to hear that. So I see electrolysis and organic chemistry in the chat. So like I'll think about those and kind of plan accordingly. So I prepare for electrochemistry for that for March 13th. And then we'll go from there. Okay. All right, guys, have a great week. Have a great week. Yes, Elizabeth. Yes, it was great having you too for these past 4 weeks. So have a great week now and follow us on Instagram. Stay in touch. So you can see what's going on. I'm gonna put the Instagram link in the chat. So you can just click it directly and follow us there. And then of course, we're on YouTube too. We're streaming on YouTube right now. So this will be on YouTube. So you can rewatch it if you're like, me never get that. I'm gonna go watch it again. You can watch it again. And of course, like, comment, share, subscribe, all the regular YouTube jargons. Do that with your friends and show them so you can explain things to them to let you understand that maybe they don't understand. So do that, and then I will see you guys in 2 weeks. So that will be March 13. Okay, guys? Let me put the YouTube in it too. Let me put the YouTube in it too. We're streaming live on YouTube now though. So let me put it there. So this is YouTube. Okay, so just you can follow that link to YouTube, subscribe, like, comment, share. But yeah, guys, that's it. Thank you for your attention, and I'll see you in 2 weeks, okay? And bring a friend, right? Bring a friend with you. I'll have a reward for somebody who brings a friend or bring the most friends, okay? All right, bye guys. Bye.
Bye, Miss.
Bye, miss.
Bye. Bye.